listen-only mode.
Welcome to our webinar. Before we start, let's take a moment to ensure that everyone is ready and familiar with the webinar control panel. First, you should have a control panel on the right side of your screen. You may hide this panel by clicking the red arrow button in the upper left corner of the control panel. You may expand the panel by clicking the same button. Second, you have the ability to submit questions using the chat pane located near the button of the control panel. Make sure you select the Send Questions to Staff before clicking the Send button. You will try to answer your questions during the webinar, and there's also a Q&A session at the end of this webinar. As a final remark, please note that this webinar is being recorded and will be available for on-demand playback. Let's get started. Today's presenter is Gordon Cooper. Take it away, Gordon.
Hello, everyone. I'm Gordon Cooper. I'm a product marketing manager for NXP Microcontrollers. Thank you for attending. I have with me Alan Wilson, a product apps engineer, who will be helping with questions and popping in occasionally. If you're here, hopefully you're here to learn about the new 4370 microcontroller. It's part of our 4300 family of microcontrollers, our high-end M4 microcontrollers. What we're going to do is talk about the new features. We'll talk about some cool applications and tools that are used, that this part is used for. And at the very end, we'll talk about the opportunity you have to buy a lab tool for a deep discount. So let me move on. So first of all, what is the 4370? It's a data application, in data applications that require ICs, you might need multiple chips to perform input, processing, and output. Now with the 4370, we give you many of the features that you need all in one chip. So we'll talk about these in more detail, but you can have high-speed digital inputs via the serial GPIO, which is a unique IP. We have a high-speed analog ADC, which we'll talk about. You have multiple cores, which you do some of the processing, and you have some high-speed output result peripherals, like high-speed USB, Ethernet, LCD, etc. So all of this makes the 4370 a complete acquisition on a single chip, acquisition solution on a single chip. Now, there are many applications that you would use a high-end processor for from the microcontroller, and many times with the performance you have on the multiple cores on here, you might not have to go into a higher-level Cortex-A processor. You might be able to stay in an embedded microcontroller and accomplish what you're hoping to accomplish, given the peripherals and performance that are available. So let us move on to some of the details. So as you look at the block diagram, it's a little hard to see, but what we'll do is highlight some of the key features. I'm assuming those in attendee fall into two categories. One, you're already familiar with with NXP's 4300 family of processors, and you're interested in what is different. Or second is you're kind of new to the whole family, and you're not familiar and you're just learning for the first time. So let's assume that you aren't familiar with our microcontrollers. The 4300 is the M4 class of processors. It's 204 megahertz with an M4 core. Now the M4 core has a floating point unit with it, or an M4F as you might see it listed. We have two versions of our 4300 family, a flash and a flashless version. This is a flashless version, and it has a very large SRAM. The flash version is available in other members of the family. So with the flashless version, how do you add program code? We'll talk about the SPI flash interface. But first, the new features, if you're just interested in what's new, we've added to our 4300 family, in addition to the two 10-bit 400 kilosample ADCs, we've added an 80 megasample ADC. And this is extremely fast, obviously, and it's what allows you to get very fast digital analog inputs. We'll talk more in details. The second significant thing we've added in the 4300 is this Cortex-M0 peripheral handler. It is basically another core. an M0 core that is not part of the same bus as the other M4 M0 core. It allows you to have a subsystem, if you will, with some dedicated memory that can control an interface called a serial GPIO. Now, serial GPIO is a way of getting rid of bit banging. It's a way of interfacing to non-standard interfaces, or it's a way of having another I2S or another SPI or another UART, etc. And we'll talk about that in more detail. So here's the cores that you have on all of our 4300, the floating point unit with the M4 core and a Cortex-M0 coprocessor. When I say coprocessor, because both of them sit on the same bus, run at the same speed, which is 204 megahertz, and you would partition your tasks up. The M4 might do your number crunching, your M0 could do your I/O handling, it could do a USB stack, for example, while your M4 core is cranking away on some signal processing, for example. On this part, and on many of our 4300 parts, you have some memory buses. We have an external memory controller that allows you to access external SRAM or SDRAM. Depending on the size of the package, it could be anywhere from 8 bits, 16 bits, or 32 bits of an external memory controller. So it allows you to scale your external memory. You also have your SPI flash interface. Now that's unique to NXP. The SPI flash interface basically connects to a quad SPI flash memory. Now you can get those from a lot of different places, Micron, Spansion, etc. The quad SPI is an inexpensive 4-bit memory, but it's a 32-bit microcontroller. So how do you use a 4-bit memory? Well, the SPI flash interface makes that 4 bits look like a 32-bit bus internally, which means you can execute code from it, you can directly access it. So it's an easy way and an inexpensive way to scale your flash code by dropping in whatever size of quad SPI that you're interested in. And finally, we've got timer, graphic LCD, and Ethernet MAC, just to name a few of them. All right, the 4370, the members of the 4300 family, we see potential applications in certainly in signal processing because it has the M4 core, industrial automation, current measurement, spectrum analysis, etc. I'm always amazed at the interesting applications some of our customers come up with. So this is the starting list, if you will, but the end more is probably the things that will be fascinating that people come up with to use this very fast ADC and all the advanced peripherals that are available.
Hey, Gordon, this is Alan. Can I interrupt you for just a moment?
Yeah, please.
Several questions have come in asking if the material is going to be provided for those who have joined.
Yes, we will make the PowerPoint available, and I'm trying to think the easiest way to. I think at the very end we've got some links, and that'll point you to the right direction. We have 2 places to find stuff from NXP. First is nxp.com, of course, and we have product pages for the products. And then we also have lpcware.com, which is probably where we'll post this. So we'll mention that at the end, but yes, we'll make this available.
Thanks.
Good. And, as Alan mentioned, if you have a question, please type it in. If it's something that we can answer easily, Alan will type in an answer, and otherwise he'll either interrupt me or we'll go through it at the very end. Here's a better view of the block diagram, typical NXP block diagram. Now there's a couple things to mention here on the cores. So this actually truly has 3 cores of performance. So it has the Cortex-M4 core, and basically we think of it as an M4 processor because it is, if you're looking at what else is out there and looking at the Cortex-M4, this will be faster than just about anything else out there, that 204 megahertz. Now, what about the other cores? Well, I really think the other cores as coprocessor. What really is nice about the M0 in the top left is that you can use it for partitioning a lot of your I/O handling. Or, quite honestly, from our point of view, it's such a small thing for us to add. It's not easy to add it correctly, but to add that a lot of our customers say, that's great, but I'll just use the M4 core and I don't need the M0. So don't think of this as something that you have to use the M0 core. Really, the M4 plus all the peripherals, I would say at least half the customers just like it for that, and the M0 coprocessor is future, code proofing, if you will, future proofing of the device. Now the packaging, as you see in the bottom right, this is unfortunately only offered in the BGA256 packages. Oh, sorry. So this one is all of our family members, and we have multiple packages, the BGAs and the LQFPs. So this is the standard 4300 family. Now, if I jump to the next one, you can see what we've added for the 4370. And in this case, it's the BGA256 and the 100-pin package. So you went from 264K of on-chip SRAM to 282K because some of that extra memory is dedicated to this third M0. Of course, we've added the 80 mega ADC as well. Except as we do this, it maintains pin compatibility. So this part is drop-in compatible with the 4350, the 4330, the 4320, the 4310, and all of our 1800 parts. So if you have an 1830 or an 1850, depending on the package, of course, this part would be drop-in compatible with those. And we also have our flash parts. So a 4337, for example, which is the equivalent with 1 mega flash, this would be a drop-in replacement there as well. And as far as the pins, there's pin muxing, so any pin could be up to 8 different things. We have a pin muxing tool to help you figure out, well, what do you really want it to be, so you can keep track of your pin out. Okay, I've already talked about the new features. So basically, it's like our 4350 with an 80 megasample ADC added and this new Cortex-M subsystem, or peripheral handler as we're calling it, which basically adds a little bit more of SRAM and is in a dedicated bus area with serial GPIO and one more SPI. Here's a quick overview for those of you who are interested in M4 in general. Now, our M4 family of processors are kind of divided into 2 groupings. If anybody's familiar with our very successful LPC4370 family, it's an M3 family. The LPC4000, shown in blue here, is our pin-compatible version of that. So if you've been using or looking at a 1788, for example, you can drop in a 4088 pin-compatible into the same socket, and what you then gain is replacing the M3 with an M4 and a floating point unit. We have the SPI flash interface working on that, and we also added a couple of analog comparators. Other than that, it's very similar. Now, in the orange here, the 4300, all of the parts within that family are compatible, and the 4370, as you see, is added here on top of the flashless family, and again would be compatible with any of the other parts here. Let's see, anything I want to mention? What we do see with the flashless parts, I do see, it's worth mentioning 2 things. One is for us at NXP, it is cheaper to make a flashless part than a flash part. Fundamentally, the way we make the silicon and the levels of metal, it's less expensive for us to make a flashless part. So all things being equal, the flashless part will have a lower price point. The second thing worth mentioning about the flashless parts is I see customers use them in 2 different ways. One, because you have a large SRAM, you can boot through the quad SPI and then only run internally, and we see some customers do that because they can have things fit into internal memory. The other way we use it, I see customers using it, is to be able to say, well, 1 meg isn't enough, or I don't know how much memory I need, or I need a lot of SDRAM, I need a lot of flash. And then what's really nice about the 4370 and any members of the flashless family is that you can easily scale your external bus through the external memory controller for data, and then expand your flash to the SPIFFy. Whatever quad SPI you plop down, you can easily get an 8 megabyte with a 32 megabit quad SPI. So all of a sudden you have 8 megabyte of flash in your system that you can execute from. Okay. Compatibility with the 1800 is worth mentioning as well, and I mentioned the 1700 and the 4000 are compatible. So it kind of shows you the overlap. So with the 4350, just as an example, that would have the M4, M0, and serial GPIO. So that one is unique to the M4, where the 1800 would have everything else, but slightly less SRAM. So what you have is a spectrum of parts that you can design the 1850 in, and then realize, you know what, I really would like a second core. I'd like a little more memory, or I want the serial GPIO because I need another SPI in the system or another UART. You can drop in replacement the 4300 family. So, worth mentioning there. Okay, the 80 megasample ADC is obviously extremely fast. What you actually have with the 80 megasample ADC is up to 6 single-ended lines or 1 differential. Now, given that you already have 2 ADCs, that brings you up to a total of 22 channels. Up to 6 of them would be 12-bit 80 meg sample, and the others would be 10-bit 400 kilosamples. So obviously it depends on your use case, whether you need that many or whether you're just be interested in the high-speed lines. Now the measurement range going in is a little bit small, so we'll require some conditioning circuitry in front of it. We do have some examples. I'll talk about the lab tool in a little bit that we've done that you can take and modify. I think that is the high-level marketing details of this. Obviously, there's a lot more information in the data sheet on specifics on the 80 megasample ADC. Okay, so unless there's some questions there, let me move on to the subsystem, or peripheral handler, as we say. And it's interesting to understand how the different cores interact with each other. So the two, in the image you see in the picture here, the 2 green boxes in the bottom left are the standard structure for the 4300 family. So basically the M4 core with its multiple buses sits on the bus matrix. And because it's on the bus matrix, it has access to all the other peripherals, as do some of the other controllers in the system. So an LCD, USB, those can all be controllers in the bus. Peripherals are slaves, like an I2C or whatever. That's not shown here, nor is the memory, but it gives you an idea of the things that can control the bus. Now, the second M0 next to the M4, as I mentioned, shares the bus. That means they have to run at the same speed, which is up to 204 megahertz. Although certainly you can run at some other speed if you don't need the performance for that. Now, what we've added is you see this little core-to-core bridge. This core-to-core bridge allows you to run the subsystem in a different frequency. And there's a lot of times that's really important and are helpful, certainly as you're interfacing to the serial GPIO or SPI, or you're interfacing to, as I said, what's nice about serial GPIO, it's basically 16 slices of I/O with shifting and clock register clocking that you can actually create your own little interface that removes the need to do bit banging. Or at least put it this way, if you have to bit bang, you can bit bang on a 32-bit word boundary instead of a bit boundary, because you can fill it up with a word, and this extra M0 that you have sitting in that bus can control the interface. We have an app note that's interesting. It uses the serial GPIO as a VGA camera input. And obviously using this M0 core and the VGA camera input, if you choose most of the M0 core, so yeah, you're using the bandwidth of the new M0, but you can actually get 30 frames per second VGA camera input using serial GPIO. So a lot of flexible, kind of cool things you can do with that peripheral. Okay, so as long as that new submaster peripheral handler Cortex-M0 is executing from the memory there, it's 0 wait state. If it has to go across the bus, you will pay a 6 to 10 cycle penalty. So if you need things on the other side of the bus to run fast, you might be using the other Cortex-M0. Now I have to say it'd be interesting to see, I've seen, I would say it's probably split right now in customers who say, hey, I like this part because of the 80 megasample ADC, and customers who say, I don't really care about the ADC, but I really like the 3 cores. So it'll be interesting to see which becomes more popular as we move forward. Obviously it depends on everybody's individual use cases and application needs. I think I already mentioned this. So this is the idea of easily being able to scale your memory. So you have 282K of SRAM on chip. You have, even if you're just using it in single core mode and you have the M4, you can expand your external memory controller by 8, 16, or 32 bits with SRAM and SDRAM. And using the SPI flash interface, it sees 4 bits of memory as 32 bits of memory to the core, therefore allowing you to actually execute code from it. we have, if you're familiar with CoreMark, I think you can go to coremark.org. Used to be a great, well, still is, I guess, a great way of comparing cores, microcontroller cores, for example. So if you want to know the difference between a ARM core and a Renaissance core or a microchip core, you can go off to CoreMark and go see some relative benchmarks for those. Now, if you're comparing a Cortex-M4 to a Cortex-M4 core, well, then essentially it's going to be identical, but what you're really comparing at that point is the efficiency of the C compiler that's being used. Pretty much all the other cores run about the same in terms of efficiency. Now, or you're measuring the clock speed, right? Because the clock speed will be different in different parts that are out there. But if you run CoreMark code in SPIFFE, comparing to run it in, say, internal SRAM, we've seen performances as good as 70% as fast as internal memory through SPIFFE. Now that is dependent on the fact that CoreMark code has some looping in it, right? So you have, essentially in SPIFFE, you have what looks like a cache, if you will, and with this CoreMark code, you can actually execute and get a lot of efficiency. If you're doing random accesses to the quad SPI, obviously you don't get to take advantage of some of the SPIFFE features, and it'll be significantly slower. So if you're running code, sequential code with some looping, you'll have very good performance. If you're doing random accesses, not as much. Some of the other features that are worth mentioning on the 4300 family and the 1800 family include USB. So if you're interested in USB, there are 2 USB ports. What's unique about our family is we have a high-speed PHY, internal PHY built in, which means if you wanted to have a high-speed USB interface, you would not need to add any external circuitry. You can attach it up right to the 4300. If you wanted 2 high-speed USBs, you can also do that, but you'd need the PHY added externally, and we have the hooks to do that. Now, if you didn't want high speed and you wanted full speed, that's fine. You can have two full speed USB device or hosts as well. And we do see some people choose the parts simply because it has 2 USB host capabilities, which is a nice thing to have. We have software libraries. We have a lot of examples. We have a lot of information on USB. So quite honestly, I think we have a very strong position with USB capabilities, not just with the 4300 family, but all the way up and down our microcontroller line. If you want something really on the low end, you can look at an LPC11U, which is a Cortex-M0 with USB attached. We see that get a lot of use in gaming mice and other applications. Another advanced peripheral is the LCD controller. It's a graphic LCD controller. It's on the 4370. If you wanted to interface to a color display, you can do it through this graphic controller. We can go up to 1024 by 768 resolution. I would say typically people have smaller resolutions they use when we have customers design this in. It's the same IP that's on our very successful 1788, our 8X family and 4088. It is also on our 4350 and our 1850. We have 10 and 100 megabit per second IEEE Ethernet that's on there. We also have software for stack support and a bunch of third parties if you need some more robust stack software. I mentioned serial GPIO, so I'll skip over that one. I think I've mentioned that multiple times. The state configurable timer is something that's also unique to NXP and also a really configurable interface. Think of it, though, as a PWM machine. You can have it be multiple timers, multiple PWMs. We have a tool in our software that allows you to create a little state machine and really custom make any timing interface that you want. It's so flexible, in fact, that we have one of our clever apps engineers, this one based out of China, who figured out a way to have a VGA camera input using the state configurable timer. So we have kind of competing camera interfaces, one using SCT and one for serial GPIO, which kind of highlights the flexibility of these peripherals. Okay, so for applications and solutions, obviously one of the unique things about the 4370 family specifically is the way how you can get things in and off the chip very quickly. So with an 80 megasample ADC, you can bring analog data in very quickly. And we'll talk about this logic analyzer oscilloscope application, but this is, if you will, kind of a whether you're doing telemetry or some other application where you need to get data on quickly, you can use the ADC for that. Now with serial GPIO attached to the extra M0 core, you can bring your digital data on very quickly, and whatever interface that you need to custom make for that. And I mentioned the camera inputs as well. So the M4 and the M0 can do a lot of the data movement on the M0, for example, or number crunching on the M4, or maybe some basic filtering. Obviously, depending on how fast you're bringing megasamples of analog data in, determines how much bandwidth you have to do something with that data. If you bring it in, you might do some basic filtering, or you might just pass it along through the USB. And the benefit of having the high-speed USB with a built-on high-speed PHY is that all in one chip you can actually get things on and upload them somewhere if you're doing, for example, to a PC. So this is basically, minus the camera input, basically what you're going to see in this lab tool that we'll talk about in a few slides. Oh, I lied, in one slide. Embedded Artist is a third party that we work with, and they came up with a very clever use of the 4370. Basically, they've created a logic analyzer oscilloscope and a signal generator using this one-chip solution, if you will. So basically, they've got a 10-channel logic analyzer and a 2-channel oscilloscope taking advantage of the ADC and the serial GPIO inputs. The signal generator actually is used our very low-end Cortex-M Plus LPC4370, which is also on the board. But in terms of what the 4370 is doing, it's the logic analyzer oscilloscope and the connection back to the PC. Now, at the very end of this webinar, I think I have a list of, I'll show you a picture, a more detailed picture of what you get. Because you're attending, you'll actually have a chance. I think it's the first 200 people who go to a link will be able to take a very short quiz, which, if you even paid half attention, should be very easy for you to answer. And then you'll get a link to get a deep discount on purchasing one of these from Embedded Artist. There's a link there. Again, we'll provide these slides, but you can go to embeddedartist.com and get more information on this as well. So the 4370, or maybe one of the other 4300 parts, also can do quite a bit with audio. There's an audio PLL. There's multiple I2S built in. We have example software. We're using GPIO to be for I2S, just as an example use case. So here's an example where the 4300 family is communicating audio from the PC, streaming audio. Typically, you probably do that at full speed if you're just doing stereo, but if you're doing multiple channels, you might need high-speed USB for that. The M0 is handling the interface, and the M4 is doing signal processing, basically. I should never assume that if you're not that familiar with an M4, Cortex-M4, it is basically identical to a Cortex-M3, and the M3 is, if you will, a next-generation ARM7, so a basic microcontroller. So the M3 to the M4 provides you with really three things. It added some signal processing instructions, if you will. It's basically a single cycle multiply accumulate, which is very helpful if you look at that biquad filter. If you're doing signal processing, that inner loop of multiply accumulate is very important to have in one cycle. The M3 can do it in 3 to 7 cycles. The M4 can do it in 1 cycle. You also get some SIMD instructions, which the compiler doesn't really take advantage of, but you see those in optimized libraries typically. And you also get a floating point unit, so making this the M4F, if you will. If you don't need any of those things, the M3 is as good as the M4. There's no extra, horsepower benefit, etc. if it's running at the same speed. If you do need those things, it's certainly nicer to have the M4. So anyway, that makes it very good for signal processing, which in this example you'd be doing some kind of virtualization of your 2 channels to 7.1 audio, and then of course from there, serial GPIO can be multiple I2S pumping out to audio. Now, I'll be honest, this is probably not a 4370 application unless you're using the ADC or the extra M0 for something else in parallel. You'd probably use a 4320, which would be a smaller package, probably slightly less cost. But it's an example of what you can do with the 4300 family. Okay, software and tools. First of all, if you're developing software for for ARM processors, there's a couple options that usually pop to mind pretty quickly. You probably would look at Kyle or IAR. Those are probably the most common, depending on what you're familiar with. We do have a lot of people who like GCC-based tools or people who like really inexpensive tools. So we offer the LPC4370 IDE. It is something that we originally partnered with Code Red. We acquired Code Red, so in fact they're now internal to NXP. So this is our NXP offered tool. We are actually tool agnostic. We're happy for our customers to use whatever is best for them. But we also understand, particularly on our low end, that if you're used to the 8 and 16-bit space, inexpensive tools are very important. So the LPC4370 is actually free up to 256K of flash or memory. So if you're using one of our low-end processors, that means it's basically free, period. If you're using the higher end, like the 4300, it would be $495 if you want to use the full memory space, and then you have a tool that supports all of our processors. So again, you might choose this. You might already have an IAR or a Kyle license, and we have some other third parties out there that support our other tools as well, TALC and some other things that support our microcontrollers. But it's worth mentioning that the three tools I mentioned all support the multi-core. So if you're interested in the multiple cores of the 4300, I would start with one of those three. All right. In terms of development tools, this 4370-based Link 2 board is kind of a cool thing. It has multiple uses. It is a 4370. You can see the small 100-pin package there in the top middle of the board. Now the 4370 and the 100-pin package you can use as a development board with this Link 2. So if you bought a Link 2, you could hook up your debugger and do some development work for the 4370 based on this board. It also, however, is a debugger. So if you had two of these, one could be the debugger, and it's, I think, $20 or so if you buy it from us, and you can make that debugger look like a Simsys DAP tool. You can make it look like a Sager J-Link, or you can use the Code Red RedLink, which of course is now our LPC4370, having brought them internally. So it is both a debugging board and a LPC4370 platform, which is kind of a cool feature. Again, if you already have a debugger, great, then you can use this for a development board. If you don't have a debugger, here's a very cheap way to have one that will work on any NXP microcontroller. We have a whole ecosystem, and one of the great things about choosing an ARM microcontroller, obviously, is the ecosystem that comes with it. And so we have a whole ecosystem of third parties that support our microcontrollers, whether it be an IAR board or an embedded artist board or an IAR toolchain or Micrium OS. Embed, if you're familiar with that, is a really cool little platform, FreeRTOS, etc. So a whole bunch of support that you get by choosing an ARM platform. Okay, so where do I find out more information? How do I get support? I mentioned two websites. Obviously, nxp.com is where you would go for all NXP-related documentation and news. So as you see the second couple links here, the product pages are on nxp.com, and you see the two packages. The 4370 FET256 is basically means it's minus 40 to plus 85 in a BGA package, 256 pins. Now, we also have LPCware, which is a NXP-owned and sponsored site that is our engineer-to-engineer forum, if you will. So if you go to lpcware.com, you can go to the forum and ask questions, and our apps engineers and other people will jump in and answer them. There is a technical support link there at nxp.com. And specifically for the Cortex-M4, the very first link there, Campaigns Cortex-M4, is more information specifically on the 4370. We had some people kick the tires, if you will, and give their opinions of the 4370 and the lab tool. So that's some interesting information you can find at that site. So that's sort of a specific to the M4 and to the 4370. Actually, the whole 4300 family. And last thing to mention at the very bottom is training videos. If you go to nxp.com LPC zone, or quite honestly, if you go to youtube.com/LPC zone, you'll see just a whole bunch of videos of myself or other people talking about, hey, here's the processor, here's this new feature, here's this demo. So a lot of information that can be found there. So here's the, hey, great, I like what I've seen, how do I get started slide. The 4370 is in full production and available now, and at your local distributor. You can go to DigiKey Mouse or Newark if you wanted to just. That's always an interesting sample of, is it real? I'll go to DigiKey, and if there's stock there that must be real, well, it's real. So you can go there and look, and then look at boards or samples from your local distributor. The Link 2 board is available. If you're interested in a higher performance Kyle board, the 4357 is the flash-based version of the part. You won't get the ADC, but you can do some development with the LCD, etc. And if you're interested in the lab tool, which I've mentioned before is an embedded artist tool, so this uses the 4370 and the Link 2 board with an add-on board to create a logic analyzer and oscilloscope. You can buy it with or without the Link 2. Maybe you already have a Link 2, or maybe you, I guess you'd have to already have one to make that useful, or you can buy it bundled. Now, that is what we're going to give you. I think it's $129 or 99 euro, but we're going to basically, for the first 200 people, let you go buy it from Embedded Artist for, I think it's $19. If you go and answer those 6 very simple questions, and then you'll get a link and a voucher that you can go and plug in as a coupon code and get a significant discount of going to purchase that from Embedded Artist. And of course, the software is available if you're interested in buying the software from us, or you can of course go to one of our third parties, or maybe you already have the software. If you do, by the way, have Kyle and IIR, I would suggest that you would need the latest version that would have support for the new processor and the multi-cores. And here's a lab tool. It's probably one of the early ones. I don't know what the number 18 is, but you can see on the top there, what you're looking at is the back of the Link 2 board, and the cables and the board that plugs into Link 2 is what is considered the add-on board that makes it a lab tool. So what's kind of cool about this is that, as I think I mentioned, with the Link 2 board, you've got a development board for the 4370. You've got a debugger board, which you can unplug it and use as a debugger, or you plug it onto this, and now you've got a logic analyzer oscilloscope. So with this one sort of combination of parts, you get multiple things that you can go do with this lab tool Link 2 combination. So oscilloscope, logic analyzer, signal generator, signal pattern generator, all for the $129 price. But for you, a special deal if you're one of the first 200. So at the end of this webinar, or shortly after the end of this webinar, you will get an email saying, hey, thank you for attending. If you click on the link that says, hey, I want to take the quiz, it's 6 questions, pretty much straightforward. We talked about pin compatibility. We talked about speed of the ADC. We talked about speed of the microcontroller, 204 megahertz. We talked about the uses of what you can do with the lab tool Link 2 combination. So piece of cake. You won't have any problems with it. And then you'll get a voucher that, again, you can go to the Embedded Artist site and order the tool, type in your coupon, and get a great discount. I think that brings us to the end. So first of all, thank you very much for attending. Hopefully it was interesting for you. And again, if you're interested in the 4370 family, the 4300 in particular, or the 1800 or any members of our family, you're welcome to check out the website for more information at nxp.com/microcontrollers, or some of the other links I mentioned before. And now, with plenty of time left, we're at the 40-minute mark, I will say, are there any questions?
Yeah, Gordon, there are a few questions that I'm still working to answer in the list that are coming across. One is concerning random access through the SPIFFE interface
Yes.
and using at the same time the quad SPI externally, for example, in a graphics application. This is a good question. A lot of times in a graphics application where you have images stored externally, those are typically accessed in a linear address mode or contiguous addresses where you have one file, for example, that contains an image. So you'll get best performance actually by accessing the quad SPI flash in a linear fashion like this. Now the reference to random access is, for example, when executing code from the quad SPI flash, since code is not frequently linear. In that case, you have mostly random access, in which case the buffer for the quad SPI
actually,
interface.
I would say code actually is pretty sequential, right? Because you're executing code sequentially, and then maybe you have a loop, and the loop could be captured by the, if you will, the cache circuitry. So code is actually pretty good too. Where you really get in trouble is if you have a table of data, and the data is random access into that by the word basis. So right, you might go to some random word, go get the word, have another lookup table that you go get a random word in some other location. When you have that level of random access, you really get no benefit of the accelerator built into SPIFFE. So I think if you're executing code, you're in pretty good shape, particularly if there's any looping going on. And if you're accessing a large image, as Alan said, you're reading it sequentially, no problem there as well. It's only when you do truly on a word boundary random accesses that you won't have any benefit. Think of it as continually cache missing if you do it that way. But
excellent.
Sequential accesses or looping of code, and you're in very good shape.
There's one question about external NAND interface. Gordon, you want to address external NAND?
Yeah, we don't have the error correction built in for NAND access. If you have a NAND that has that built in, I think if I'm thinking of this correctly, so typically we see people use SDRAM when interfaced to the external bus.
There's a question about the cache size for the quad SPI.
Yeah, I mentioned cache, but it's basically something that's internal. It's not something that you would have to worry about going in and maintaining or manipulating, so it's sort of buried into the IP. So I mention it to give you a visual of what's happening, but those details we kind of leave. To access the quad SPI, we give you API calls. So we also, early on, because of worrying about the competition, we didn't provide a lot of details. I think we're a little more flexible about that and can provide the code that goes behind the API calls. Originally, it was just the API call. So I guess my answer to that is we don't really talk about the cache size, and it's not something you can access or influence anyway.
So in that sense, it's not a traditional
right.
use of the word.
I mentioned it. Think of it as an accelerator. I mentioned cache because most people know what that is and kind of visualize how it would work.
Are there plans to include larger amounts of internal RAM?
That's a great question, and it's interesting. One of the reasons we were able to get so much RAM is there's no flash, right? Because at the end of the day, the die size is what drives the price for us, package as well, but fundamentally the size of the die. So we've had customers who said, this is great, when can I get 512K of flash? And I would say there's always some trade-offs for us in terms of next-generation products, and we're taking inputs. But at the moment, although I've had some requests for larger SRAM, there's nothing in the immediate future that will be coming out with larger SRAM.
Okay. They can always expand externally, right?
Yeah, absolutely. In fact, that's tends to be what we see. People will say, hey, this is great, I've got the external bus. Particularly if you're using the graphic LCD, you'll need the external memory anyway for your frame buffer. We've seen people who are future-proofing and saying, well, I'm going to put some memory out there. I don't know how much I'm going to need, but I will be able to expand it as I go. Now, obviously, that's not for everyone. If you're cost-sensitive, you don't want to just randomly slap some external memory on there. You want to run from internal and not have to worry about hooking things up externally.
Right. There's a question, is the external flash mapped to the CPU's address space? And that answer is yes for all of the supported external flash types, especially, as Gordon was mentioning, the quad SPI interface through our SPIFFE module. And it also maps the entire content of that flash to an addressable location in the address range.
Yep. Yeah, I usually mention that, but yeah, it's memory map, which is what's really cool about it. Even though it's 4 bits to the outside world, to the core, it looks like a memory map 32-bit location. Great questions. Anything else?
We have some comments coming across, but I think that's all of the questions right now.
Okay, well, excellent. Let me thank you again for attending, and let me go back to the, what happens next. So again, you'll get a thank you email, and in that thank you email, please look for a link. The quiz is pretty straightforward, nothing you couldn't pretty much read out of the data sheet. It's just to make sure you're paying attention instead of somebody randomly popping up against the quiz. And then after that, you'll get a voucher. And I'm not sure. I think they email it to you, or maybe it pops up and you print it out. I'm not 100% sure how that works. And then from there, you can go get one of these cool little lab tools. And even if you don't develop on the 4370, it gives you a little logic analyzer you can sit on your bench or oscilloscope. So kind of a cool thing to have. So thank you again for everyone attending. And I would point you to the website, and certainly you can go to the forum on lpcware.com. There should be some activity there if you can ask further questions. And thank you again. Have a great day.
Thank you for your participation in this webinar. Tomorrow you will